Hello everyone, welcome to today's webinar, Elastic Load Balancing Deep Dive. Before we get started, I have a few housekeeping items. On the right side of your screen, you will see a Q&A window. Please use this to submit your questions for our presenter and moderators at any time, and we'll address them while they come in. At the conclusion of today's presentation, there will be several poll questions preceding the live Q&A. Please take a moment to provide us with your feedback when you see these poll questions appear on your screen. Today's session is being recorded, and the next few days we will send you a follow-up email with the on-demand links to the presentation deck and webinar recording. Again, welcome to today's webinar, Elastic Load Balancing Deep Dive. Our presenters today are Narayan Subramaniam and David Pessis. David, welcome. The floor is now yours.
Hey everybody, thank you so much for listening to our webinar today. My name is David Pessis. I'm an engineering leader on the Elastic Load Balancing team, and I've been with Amazon for just over 4 years. And I'll be doing this presentation with my colleague Narayan. Narayan, please introduce yourself.
Hello, I'm Narayan Subramaniam, and I'm a product leader at Amazon. Been with Amazon for a little over 4 years now, and we're excited to be doing this Elastic Load Balancing Deep Dive with you today.
All right, so we'll jump right in here. So this is the first slide. This is the only slide that I'm actually going to read directly out of the presentation. This is just to define for everybody exactly what load balancing is. Elastic Load Balancing automatically distributes incoming application traffic across multiple targets, such as Amazon EC2 instances, containers, and IP addresses. And for those of you who follow the Elastic Load Balancing service closely, we recently add IP addresses as targets for the Elastic Load Balancer. So the Elastic Load Balancing family, we have 3 different products. All the way to the left here is the Application Load Balancer. This is really what focuses on the HTTP and HTTPS layer 7 requests. This is our newer product that we released roughly a year ago. In the middle here is the Network Load Balancer. This was released approximately 2 months ago, and this focuses on those TCP layer 4 workloads. And finally, we have our Classic Load Balancer. This is our original load balancer product. This is the previous generation that can actually do HTTP, HTTPS, and TCP. Today's presentation is going to focus primarily on the Application Load Balancer and the Network Load Balancer, and we'll briefly discuss some differences versus the Classic Load Balancer as we go through the presentation. So there are the four main characteristics of the Elastic Load Balancing family that we like to hit on are these four characteristics before you. First and foremost, Elastic Load Balancing is elastic. And what that means is once you create your load balancer and as you begin ramping up traffic and sending additional more requests through the load balancer, we will automatically throw more resources and compute power at that load balancer to accommodate those increases in traffic. Next, we're secure, and as you'll see shortly as we walk through this, we have teams of principal and security-focused engineers that really look at the best cipher suites, the best security to give you guys to your load balancers so that you guys can focus on building awesome applications and let us do that very complicated security work for you. Next, we're integrated. And so what this means is that when you use Elastic Load Balancing, we're tightly integrated with services like CloudWatch, auto scaling, and different logging services. And so by using ELB, you get access to you were deeply integrated with a lot of other AWS products. And finally, we're cost effective. And so if you look at the cost of you operating your own load balancer, let's say you spin up a bunch of EC2 instances to handle your load balancing and try to manage that yourself, by letting us do that for you is significantly more cost effective than you doing it on your own. And so we've all been here before. I love this picture. When we're all building an application for the first time, we'll have one server or one EC2 instance where we put the database, the application server, the firewall, all on that same instance. Obviously, this is not a recommended architecture to build a highly available or fault-tolerant application. But again, we've all been here. What we like to see is something like this, where you put a load balancer in front of your application, you have multiple targets behind that load balancer, and so in the event that one of those EC2 instances or targets fail, the load balancer will automatically fail over to the healthy instances behind the load balancer. And so this is a much healthier architecture, much more fault tolerant in the event of an issue with your application. And so we're going to walk through, like the foundational architecture of the load balancer products. So we'll start here with your VPC, the customer's VPC. And when you are creating a load balancer, we highly recommend that you give us 2 different availability zones. And so you'll give us a subnet in your VPC and 2 different availability zones. And in each of those subnets, we want you to put targets in those subnets. And this, again, we'll get into details here, but this is to really facilitate you building a fault-tolerant application. Next, you look at the ELB VPC. And again, we use VPC the same way you, the customer, use VPC. And what we will do is we'll put load balancing capacity in a subnet that correlates to the subnets where you have put your EC2 resources. And finally, in front of the ELB, we put Route 53. And so when you create a load balancer, we will give you an A record. And that A record will actually do a round robin to the different load balancer capacities in front of your application. And so every time a call is made to Route 53, it's going to do a round robin between those 2 load balancer nodes. And then those load balancer nodes can then route traffic to your EC2 instances. And so you can see in each of these layers, we have very high levels of fault tolerance, because in the customer VPC, if one of those subnets has an issue, the load balancer can still route traffic to the healthy subnet. And on the ELB side, if one of those nodes has a problem, Amazon Route 53 will automatically fail away from an unhealthy load balancer node. But so again, this high-level architecture here gives us extremely high availability. So right now, we're going to do a deep dive. We're going to start with a deep dive into the application load balancing product. The application load balancer was launched roughly a year ago. It's a very feature-rich Layer 7 load balancing platform. One of the key characteristics here is the ability to do content-based routing, which actually allows you to route traffic to different applications behind the load balancer. And so this really allows you to get into more of a microservices and container-based application architecture, which really allows you to consolidate and put more of your applications behind the load balancer. So a little more detail on the application load balancer. We have native support now for WebSockets and HTTP2. As I just mentioned, we have path and host-based routing, and we'll get into more details here in a moment. We have improved health checks, additional CloudWatch metrics. ALB is very good for real-time and streaming applications. We've introduced a brand new API. And finally, load balancer deletion protection. We have some stories where customers have accidentally deleted their load balancer, and they call AWS frantically to ask us to help restore those resources. And so now, just like you have with an EC2 instance where you can protect that from being deleted, you can also do that now with your load balancer. So right now, we're going to go through we're going to build a load balancer architecture together using ALB. So when you start with a load balancer, every single load balancer needs a listener. And so what is a listener? A listener is a port and protocol combination which the load balancer must listen on. As an example, port 80 and HTTP, or port 443 and HTTPS. These are typically the most common listeners that you're going to set up on an ALB. You need at least one listener on the application load balancer to accept traffic. And the load balancer can have up to 50 listeners. And then finally, we have routing rules. And so this is that content-based routing, that host-based routing. Those are defined at the listener level. And we'll get into that in a moment. So on the load balancer, again, we mentioned that you're going to create your listeners. And the next step will be to create target groups. And so what are target groups? Target groups are logical collections of EC2 resources or AWS resources. These exist independently from the load balancer. These are regional constructs that can also be associated with an auto-scaling group. And target groups can contain up to 1,000 targets. And as I mentioned earlier, a target group can contain targets that are either EC2 instances, they can be IP addresses, or that can be containers. And so in this example, target group 2 has IP addresses, target group 1 has EC2 instances, and target group 3 has containers. And the other thing you'll notice here is the health check. We'll get into this in a moment, but every single target group has its own health check configuration. And this is how the load balancer can determine if a target is healthy or not, so that it can decide whether or not it wants to route traffic to that specific target. And so again, as I mentioned earlier, we support EC2 instances, containers, or IP addresses for targets. But what's very cool here is EC2 instances can be registered with the same target group using multiple ports. And this becomes convenient if you want to, for example, if you want to put your own targets, if you want to put your own containers on your EC2 instances, you can actually do that mapping manually yourself. And so you can map that same EC2 instance multiple times with the ALB, but using different port combinations. And furthermore, a single target can be registered with multiple target groups. And as I mentioned earlier, you can use IP addresses as targets, and these are accessible. The load balancer can access IP addresses that are either within your VPC or connected to your VPC via direct connect or VPN. So finally, we have this application built. We have our listeners, we have our target groups, we have our health checks, and now we're going to add rules. So as I mentioned earlier, the rules are defined at the listener level. And so the first type of rules we have is the first is the content-based routing. And so when a rule, each listener has one or more rules, and so when one of those rules match, we'll take an action, and so we'll route to the appropriate target group. And so the example I want to show you is, in the path, if the path is API, we will send those requests to a specific target group. If it's david.com/images, we'll route to another, we can route to a different target group. And so here is some of the format of the rules. This is the syntax required in your path. We're not going to get into that now. This is pretty standard, but you can see the syntax that's required in the path, which will then make up your rules. And so typically today, let's say you wanted, with the classic load balancer today, if you wanted to have two different applications, if you went in orders.example.com or images.example.com, you would actually need to create two different load balancers. And so here you have two classic load balancers, one that's handling one application, one that's handling the other application. Obviously, this is twice the administrative burden, and this is twice the work, twice the configuration. Now with the application load balancer, we can now consolidate these applications behind one application load balancer. And so as I mentioned earlier, with that path-based routing, you could do example.com/images, and that's going to be routed to this target group. If I do example.com/orders, that's going to be routed to this target group. And so we mentioned earlier with this microservices architectures, you're really able to consolidate applications behind your load balancer, behind your application load balancer. One thing I want to point out is, a lot of customers get very excited because, they can do this huge consolidation and save money. But I also want you to be careful and think deeply about how much consolidation you want to do. One of the things that we like to recommend to our customers is do a load balancer per department. If you put the entire company behind one application load balancer and one engineer accidentally changes a configuration, you can actually do a lot of damage. You could potentially bring down a lot of these applications. And so really think about that blast radius and that control and how much you want to consolidate, because you want to be careful, again, to not have a massive failure across the company. As I mentioned earlier as well, your target groups can be associated with an auto-scaling group. This is a very cool feature because each microservice or each application behind the application load balancer can scale independently. And so if target group 1 is getting the bulk of the traffic, auto-scaling could just focus on scaling the targets in target group 1. So this is a very nice way to efficiently and cost-effectively scale your application where you're only scaling where you're sending additional traffic. ALB is deeply integrated with ECS. This is our container service, and I mentioned earlier how you could actually carve up your EC2 instance into containers. With ECS, this is all taken care of for you automatically. And so we talked about that port, how you have to manually add each port to the configuration of the load balancer. With ECS, all this is taken care of you automatically. And so ECS makes it very easy to use containers behind your load balancer, and allows you to be very efficient in the way that you use your resources. So as you can see here in this architecture, if I go to example.com/API, we go to this target group up here, which is all EC2 instances. If I go to example.com/test, we'll go to another target group that's comprised of containers. I mentioned earlier that you can also have IP addresses as targets. Each target group is homogeneous, and so you can't have mixtures of EC2 instances and containers in the same target group. And so you need to have they have to be all EC2 instances or all containers or all IP addresses. This happens to be one of my favorite features is health checks. Health checks allow for traffic to be shifted away from failed instances. And so I'll show here, in this example here, we're pretending that top target is becoming overburdened. And so let's say that top EC2 instance, for whatever reason, it's having problems. And the CPU is extremely elevated. And the ELB, you guys have configured your health check on that load balancer. The load balancer is going to start recognizing that target on top here actually begins to fail that health check. And what will happen is the ELB will now fail away from this target and only send traffic to the two remaining healthy instances. So this is a phenomenal feature because you as the engineer, if you deploy a bug or there's an issue with the specific instance, the ALB will automatically take that out of the rotation and fail away from that target. You will then get a notification so that you can go fix that issue. As soon as you put that target back in, you fix that target and you add it back to the load balancer. The load balancer can then begin routing traffic to the healthy node again. So I'm going through here. You can see the animation, how the load balancer failed away from that unhealthy target, and then it begins sending traffic back to the target as it becomes healthy. And so on ALB, we support HTTP and HTTPS health checks. You customize the frequency and failure thresholds. And so how many times, how often do you want to ping that target? And then what constitutes a failure? Is it 2? Is it 3 failures in a row? And then you really need, I really want you guys to think deeply about the depth and accuracy of your health checks. I'll give you an example. You don't want the health check to be too shallow, where you might detect the target as healthy, but it really isn't. And so if it's a very light HTTP check, that might come back healthy, but the application isn't functioning correctly, and so you mark it as healthy and you continue routing traffic to that node, you want to be very careful. On the other hand, you don't want the health check to be too deep. And so let's say, when you do your health check, it's calling the database, and the database is then, is going across every single target behind the load balancer. If that database has issues, what's going to happen is every single target behind your load balancer is going to fail, at which point the entire application is going to fail. And so you also want to make sure you don't have a dependency that could potentially take out your entire application. And so be very careful with how deep you make these health checks. Finally, you can customize which successful response code defines a successful health check. And so you can use any code between 200 and 300. And then also, the health check failure details are now returned via the API or the management console. And so you can actually see the reason for the health check failure. The other type of routing we have is host-based routing. And so earlier we discussed the path-based routing, example.com/API or example.com/images. With host-based routing, Narayan.com can go to one target group and David.com can go to another target group. And so this gives you even more flexibility in terms of your routing rules. there are several predefined security policies on the application load balancer. We have teams of scientists and security engineers that are always looking at how do we give our customers the absolute best security. And so what we do is, obviously, we own Amazon.com. We have a whole bunch of customers going to Amazon.com. We also know, what are the suite of ciphers and security policies available out in the wild. And so what we do is we look at our customers visiting Amazon.com. We look at all the security policies and ciphers available to you. And we try to find that perfect combination of what's available, what presents the highest level of security, and then we make those policies available to you. So simply, when you're creating your application load balancer, there's a drop-down, and you can simply pick the policy that you want to apply to your load balancer. In the event of a vulnerability, you've seen this in the past with Heartbleed, for some of you who are aware of some open SSL issues in the past. If there ever is a vulnerability, we will immediately patch that vulnerability, create a new policy, make it available to you here, and simply through selecting that new policy on the dropdown, you've patched your load balancer and you've patched all the applications behind your load balancer. We recently, not recently, but we have launched native IPv6 support for ALB. This is actually my favorite slide because there's nothing else I have to say here. But you can get an IPv6 address to the front of your application load balancer. ALB is also deeply integrated with WAF. And so WAF is the web application firewall that monitors requests, it protects your applications. You can block IP addresses. It also protects you. It looks for specific SQL injection or cross-site scripting. What's very cool about WAF is as this team adds more protections and more detections, you automatically get these just by the fact that you've integrated your ALB with WAF. And so when a request comes to ALB, WAF will do all these detections. It's going to monitor those requests, make sure these are good requests before allowing them to pass through your application. And again, as the WAF team continues to add features and add detections, you will just get these just inherently by using WAF with your application load balancer. So one of the features that we recently launched was SNI. Very excited to launch this feature. It's been one of the most requested features over the last 4 years. This allows you to put multiple TLS secured applications behind your load balancer. And so if you want to do HTTPS, Narayan.com or HTTPS David.com, you can now do that all on a single application load balancer, put multiple certificates on the load balancer. One of the cool things is that ALB, we automatically choose the most optimal TLS certificate for each client. And so we're choosing the best certificate that's the combination of security and speed. We support the classic RSA algorithm and the newer, faster ECDSA algorithms as well. So super exciting when you use SNI in conjunction with host-based routing. This allows you to further put more and more applications behind your application load balancer. IP as a target, we mentioned this earlier. Just to give a few more details here, you can use any IPv4 address from within the load balancer's VPC cyber range. And so, again, any IPv4 address within your VPC. You can also reach IPv4 addresses that are connected to your VPC via direct connect or VPN. And so here we talk about the specific RFC ranges of IP addresses that you can access with your load balancer. So this also includes peered VPC, EC2 Classic, on-premise targets reachable via direct connect or VPN, as I mentioned earlier. So super exciting feature, gives you even more flexibility to put applications behind your application load balancer. Cross-node load balancing is a great feature. This just comes enabled on every single application load balancer. And if you remember earlier, when you create a load balancer, we highly encourage you to give us 2 subnets and put targets in both subnets. And the reason we ask you to do that is because if an AZ happens to have an issue or one of your subnets happens to have an issue, The application load balancer, both of those nodes of capacity that I showed you earlier can route to both subnets. And so even if one of your subnets fail, both nodes of ELB capacity can still route to those subnets. And so again, this is a very neat way to make your application even more fault tolerant. So again, you guys can focus on building awesome applications while we help you build very highly available fault tolerant applications. ALB is obviously deeply integrated with CloudWatch. These are provided in every single load balancer with 1 minute granularity. One of the neat features that we added recently was percentiles. And so you can look at your CloudWatch metrics now with 99 or 90 or 99.9 percentile. But what this means, for example, is if I'm looking at the 99th percentile and I'm looking at latency, what that means is that 99% of my customers are experiencing that latency or better. And so this is a very powerful tool for you to zero in on issues that you might be having with your load balancer. When you look at averages, latency averages, it's very hard to pull out issues because they might be buried within the average. But when you start looking at percentiles, the 90th or the 99 or 99.9, you can really zero in on issues you might be having with your load balancer. So I'm going to go through, there's latency metrics, there's a whole suite of metrics that you can get within CloudWatch, and I highly recommend you use those when trying to debug issues with your load balancer. Finally, we give you access logs, and what this tracks every single request that comes through your load balancer. We deliver these to an Amazon S3 bucket every 5 or 60 minutes. And so the typical pattern is if you're seeing an issue with your application, the first thing our customers will typically do is look at those CloudWatch metrics. They'll look at the latencies, or they'll look at healthy host counts behind their load balancer. And then they'll look at their access logs. And the access log really helps you dive deep because you're looking at each request, the IP address, the request path, the server response. And you look at all of these to really help debug that issue and get to the bottom of what the problem is with the application. And finally, pricing. With the ALB, we have a new pricing mechanism. It's called the LCU. The hourly fee for the application load balancer is actually 10% cheaper than the classic load balancer. And I'm going to get into the details here of exactly what an LCU is. And so with an LCU, you get 25 new connections per second, 3,000 active connections, 2.22 megabits per second, or 1 gigabyte per hour, or up to 1,000 rules. And so we look at all these factors on an hourly basis, and then you're going to get charged for the dimension with the highest usage over the hour. So this is slightly different from the classic load balancer where we only focused on bandwidth. Now with the LCU, we're looking at connections, new connections, active connections, bandwidth, and the number of rules evaluated. And again, you're charged on the dimension with the highest usage over that hour. And finally, migrating to the application load balancer, we now publish a metric to your classic load balancer, which allows you to estimate the cost if you were to migrate to the application load balancer. Really, it's as easy as creating a new application load balancer. We'll give you a new A record. You can start attaching targets to that new application load balancer, and through your DNS, you can start moving traffic over to the application load balancer. Very recently, second week of November, we released the migration wizard within the console, where you can actually use the wizard to help really streamline way to migrate your traffic from your classic load balancer to your application load balancer. And so if you're thinking of migrating, I highly recommend you take a look at that. And so I'm now going to hand this over to Narayan, and so he is going to give you a deep dive on the network load balancer.
Thanks, David. Now that you've seen all the features related to the application load balancer that operates at layer 7, we will now take a deeper look at the new network load balancer that was launched a few months back. Network load balancer operates at the layer 4 level and uses connection-based load balancing. It supports TCP protocol. It is extremely high performant, so NLB can actually handle millions of requests per second out of box. Based on our tests, we have seen that NLB can handle 1.5 million requests per second out of box at cold start with no manual intervention needed. In addition, NLB will keep scaling as your traffic increases. This is extremely suited for volatile traffic workloads. In addition, NLB, or the network load balancer, also supports static IP and is ideal for applications with long-running connections. Network load balancer has also got very low latencies that are in milliseconds at connection establishment time and microseconds after. On the older classic load balancer, since it terminated connections at the load balancer, you needed to turn on proxy protocol to get the source IP of the client. In NLB, as it is a pass-through, it passes the client source IP to the backend and removes the need to have proxy protocol for this feature. Also, as David mentioned, on ALB, we launched a new API as it was richer in terms of resources. We are reusing the same API for network load balancer as well. You only change the type to network when creating a new load balancer. We also support deletion protection similar to what we do on the application load balancer. Let us now go through some of the other key features of the network load balancer. Network load balancer supports static IP, which is a single IP per availability zone. When you create a network load balancer, we automatically assign a single IP per AZ or availability zone. If you don't want this IP to change for the life of the load balancer, then you can also assign an EIP from your own EIP pool. If for some reason you delete the network load balancer, the EIP is added back to your EIP pool. This has been a big requested feature from our customers. Some of the big use cases for this feature include needing this for firewall purposes, where they can whitelist the IP of the network load balancer, or similarly for other customers who want to zero out the billing for customers through their carriers. As can be seen here, one can assign the EIP one per availability zone. Now that we've talked about the static IP feature, let us now go through another important feature supported by the network load balancer, which is the preservation of source IP. Since NLB does not terminate connections and is a pass-through, it preserves the source IP of the client to the backend application. This eliminates the need for customers to turn on additional parameters like proxy protocol and needing to update their applications to understand proxy protocol. They can simply use the source IP provided by the network load balancer for logging or other use cases, such as taking certain actions based on clients. Source IP is preserved only when using instances as targets behind the load balancer. So if you're using IPs as targets behind the load balancer instead of instances, then source IP is not preserved, as these IPs can reside outside the VPC as well. For these cases, we have added proxy protocol version 2, which will send the original connection source and destination endpoints to backends, and that can be used by our applications to get the client source IP. Now let's take a look at an actual firewall example, a proper use case where we can see how the static IP feature and preservation of source IP feature on NLB is very useful. In this example, we have an external web-facing NLB that is fronting a firewall, which is then connected to an internal NLB that sits in front of web service. The external and the web-facing NLB support static IP addresses, which means it uses less addresses, which is helpful if customers are whitelisting their firewalls or expecting VIP-like behavior. This is used for firewalls or third-party proxies. The web-facing network load balancer also preserves the source IP. This helps the firewalls with features such as geo-IP blocking if you want to block traffic coming from certain geos. The internal NLB that provides static IP address that don't change. For firewalls, WAFs, and proxies that must NAT traffic, this allows those devices to maintain a single address for their NAT state tables. This also allows customers, to handle less number of IPs, which means less operational plane overall. So this example, displays how both the static IP feature and the preservation of source IP feature can be extremely important for customers. As we discussed before, NLB uses the same rich API that ALB offers, which includes resources such as listeners, target groups, and targets. And David had actually explained in detail how each of these resources work on the ALB side, and this same thing applies on the network load balancer side as well. So in addition to instances and containers, as David had mentioned, we also support IPs to be load balanced using NLB as well, just as what we have on the application load balancer side. This is similar to the ALB support as well. One can use the IPs from a VPC CIDR range when IP is within a VPC, or if the IP is outside the VPC, then you can use the RFC 1918 or the RFC 6598 range. Here we show how one can have multiple target groups behind the same network load balancer, with target groups having EC2 instances, IP addresses, and ECS containers. Another key advantage of the network load balancer is its support for health checks that allow for traffic to be shifted away from failed application servers. This is extremely important for the availability of your applications and ensuring that only healthy servers can serve traffic for the customer. Network load balancer supports both network and application target health checks. With network health checks, NLB is able to stop sending traffic to unresponsive targets in a span of milliseconds. This is extremely important for fast failover applications. Network health checks uses the overall response of your target to normal traffic to determine an unresponsive target. If the target becomes unable or too slow to respond to new connections, then the load balancer will mark the target as unavailable. In addition, one can also set up application health checks on the load balancer to go deeper. These application health checks can be configured to be HTTP, HTTPS, or TCP. You can configure the frequency of the health check and also the failure thresholds that determine when a health check fails. By periodically probing a specific URL on a given target, it can integrate the health of the actual application. Let us now look at the DNS failover scenario. Here in this picture, the dotted line are the availability zones. Route 53 is shown on the top left. Since network load balancer has two IPs for the two availability zones, Route 53 resolves DNS to one of the two IP addresses. It does the load balancing between the availability zones using round robin. If there are no healthy targets registered with the network load balancer, or if the network load balancer nodes in a given zone are unhealthy, then Amazon Route 53 will automatically direct traffic to load balancer nodes in other availability zones. As can be seen here, when the targets behind the NLB in US West 1B are down, Amazon Route 53 now resolves to only the IP of the NLB that has healthy targets, and now every incoming flow is sent to the IP address in US West 1A. This ensures high availability for the customer, and NLB can handle the DNS failover scenarios very effectively. Let us take a look at visibility. If you take a look at elastic load balancing in general, we have a large number of metrics that are available for customers. With NLB, we give you 1-minute granularity metrics. These include metrics that provide insights into the traffic and capacity, errors in backend health for the load balancer. Customers can alarm on these metrics and take actions as needed. You can also use the flow logs feature to record all the requests that are sent to your load balancer. Flow logs capture information about the IP traffic going to and from network interfaces in your VPC. Flow log data is stored using Amazon CloudWatch logs. Now let's take a look at the pricing for the network load balancer. With network load balancer, just as we do for other elastic load balancing products, You pay only for what you use. There are two charges. One is the hourly load balancers charge, and then there's a usage charge depending on the amount of capacity used on the load balancer, called as load balancer capacity units or LCUs. The number of LCUs used is related to bandwidth, new connections, and active connections. We use a similar pricing mechanism for application load balancer as well. The hourly charge on network load balancer is 10% cheaper or less expensive than classic load balancer and comes to be about $16 a month. The data processing charge or LCU charges are 25% less expensive than both classic and application load balancer. Now let us take a look at what constitutes an LCU. Each LCU provides 1 gigabyte per hour bandwidth, 800 new connection or non-SSL connections, and 100,000 active connections. We calculate the LCU value for the 3 dimensions and charge you based on the maximum of the 3 dimensions in an hour. So the key here is we don't charge you for all the 3 dimensions. You are only charged for the maximum of the 3 dimensions. As customers are looking to migrate from classic load balancer to network load balancer, we offer a migration utility in GitHub. This makes it very easy to move from classic load balancer to network load balancer. We also offer a one-step migration wizard on the console that converts your existing classic load balancer resources into network load balancer resources. So the big question some of you might have is, when do I use a network load balancer? In this table, we point out the differences between the 3 products. This will allow you to select the load balancer of your choice. As you can see, ALB supports advanced content-based routing features, SNI, TLS termination. It supports HTTP, HTTPS, HTTP2, and WebSockets. NLB, on the other hand, supports TCP with static IP support and preservation of source IP. In addition, both ALB and NLB offer load balancing to IPs and containers, in addition to instances. With Classic, it is limited in feature set and can be used with classic networking use cases. So let's try to summarize this, right? So you can choose an application load balancer when you need a flexible feature set for your web applications with HTTP and HTTPS traffic. Operating at the request level, application load balancers provide advanced routing, TLS termination, and visibility features targeted at application architectures, including microservices and containers. Choose a network load balancer when you need ultra-high performance and static IP addresses for your applications. Operating at the connection level, network load balancers are capable of handling millions of requests per second while maintaining ultra-low latencies. Choose a classic load balancer when you have an existing application running in the EC2 Classic network. With that, we conclude this webinar. But now, we really thanks for your overall time today, as we covered the best practices and a deep dive into the application and network load balancer. We can now take up or answer any questions that you might have.